Hey everybody. Before we advance to the next topic in calculus, let me say one more thing about limits. And this has to do with properties of limits that we should probably remember and take with us through our mathematical studies. The first property we're well aware of, the limit of a constant is the constant itself. So if we compute the limit of a constant k, we get the constant k. The limit of a constant is the constant itself. In our second property, we have the limit of the sum or difference of functions. And that turns out to be the sum or difference of the two limits. So here we could say the limit of a sum or difference is equal to the sum or difference of the two limits. And what that really means is that if we're computing the limit of the sum or difference of functions, we can compute that limit one term at a time. So if we're computing the limit of the sum or difference of functions, we can compute the limit of the first function, and then compute the limit of the second function, and so on, and then put them together later on. In the third property, we have the limit of the product of functions. And that turns out to be the product of the two limits. So I guess I would say this. The limit of a product is equal to the product of the two limits. What this means as far as computing the limit of a product is that we can compute the limit one factor at a time and then just multiply the factors together when we're done. And analogously, we have the limit of a quotient, and that turns out to be the quotient of the two limits. So we might say this. The limit of a quotient is equal to the quotient of the limits, but there is a catch. This only works if the limit of the denominator is not 0. It only works if this thing is not 0. But what this means is, if the limit of the denominator is not 0, we can compute the limit of a quotient by computing the limit of the numerator, the limit of the denominator, and then computing that quotient. And finally, the limit of x to the n is equal to x to the n evaluated at the number that x is approaching. And this is just a consequence of the fact that x to the n is a monomial. And monomials are continuous, which means that the limit of x of n as x approaches c is equal to x to the n evaluated at c. So for x to a power, a non-negative whole number power, if we compute the limit as x approaches c, we can just plug in c for x. So now that we've been over the properties of limits, let's just do an example just for the sake of reinforcing what we just discussed. Okay, here's an exercise designed just to get us familiar with the properties of limits and reinforce what we were just told. Compute this limit using the properties of limits. Document each step. Okay. In the most general sense, what kind of algebraic expression are we computing the limit of here? Isn't this the limit of a quotient, right? And we have the property, I think it was number 4, the limit of a quotient equals the quotient of the two limits. So we can compute the limit of the numerator and the limit of the denominator and just put one over the other. So limit of the numerator is x approaches 2. So 3x squared minus 2x plus 4 all over limit of the denominator. Limit as x approaches 2 of 2x squared plus 6x minus 8. And how would I document that? Limit of a quotient equals the quotient of the limits. Okay. Now, on with our next step. In both the numerator and the denominator, we have the limit of a sum or difference, or both, right? The sum and differences of functions. And we have a property that says the limit of a sum or difference equals the sum or difference of the limits. In other words, we can compute the limit of a sum or difference term by term. So let's do that. Limit of the first term minus limit of the second term plus limit of the third term and we do the same thing for the bottom. Limit of the first term plus limit of the second term minus limit of the third term and we document that. The limit of a sum or difference equals the sum or difference of the limits. Now, in our next step, we have a choice. There are two different properties that we can employ here, and it doesn't matter which one we choose. One thing that we could do is we could say, hey, look, we have the limit of a constant, the limit of a constant. We can just employ the property that says that the limit of a constant is equal to the constant itself. But we also have the limit of a constant times a function. The limit of a constant times a function. We could use the property that says the limit of a constant times a function is equal to the constant times the limit of the function. Whoa, 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 whoa. That was not one of the properties that I put up there, was it? Okay, I'll have to add that retrospectively. That will be number 6. Huh, shame on me. For right now, we'll apply the limit of a constant is equal to the constant itself. So we have equals limit x goes to 2 of 3x squared minus limit as x goes to 2 of 2x. And then we have the limit of a constant. 4 is the constant itself. Okay. And in the bottom we do the same thing. Limit as x goes to 2 of 2x squared minus limit as x goes to 2 of 6x plus the limit of the constant 8 is just going to be 8. And to justify that, we will say the limit of a constant is the constant itself. Okay, very good. And now we apply that property that I didn't list on the board. I'm going to have to make up for it at the end of this lecture. There's a property that I didn't mention, but I'm going to use it now. And that property tells us that the limit of a constant times a function is equal to the constant times the limit of the function. So the limit of a constant times a function, let's say k is a constant, is equal to the constant times the limit of the function. And what that means essentially is that if we're computing the limit of a constant times a function, we can take this constant factor and we can move it out in front of the limit sign. That's what it means. So let's apply that to all 4 of these terms, because each one is the limit of a constant times a function. The limit of a constant times a function is the constant 3 times the limit of the function, which is x squared, minus the limit of this constant times the function. The constant is 2. So we're going to get the constant 2 times the limit of the function Okay, same thing for the bottom. We have the limit of a constant 2 times a function x squared. That we can write as the constant 2 times the limit of the function. 2 times the limit as x approaches 2 of x squared minus, we have the limit of a constant 6 times the function x. We can write that as the constant 6 times the limit of the function x. 6 times the limit of x. And we will document that. Okay. In each case here and here, we had the limit of a constant times a function. We rewrote it as the constant times the limit of the function. Now I guess there's just one thing left to do. Do you know what it is? Limit as x approaches c of x to the n equals c to the n. So we just plug in for x now. So we'll have 3 times the limit of x squared as x approaches 2, so that's 2 squared, minus 2 times the limit of x as x approaches 2, so we'll plug in 2 for x. And then on the bottom, 2 times limit of x squared as x approaches 2, we'll plug in 2 for x. Somewhere along the way, plus, 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 plus. Somewhere along the way, my plus turned into a minus, like right here, and right here. Okay. 6 times the limit of x as x approaches 2. So we plug in 2 for x. Now we're only computing the limit this way because the directions told us to. If we're not given these specific directions, we don't compute the limit this way. But let's see what we have. 4 times 3 is 12, minus 4 is 8, plus 4 is 12. Okay, 2 times 4 is 8, plus 12 is 20. Plus 8, son of a gun, minus, 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 plus. I don't know why people think I'm dyslexic. Okay, this should be a minus here, okay. And a minus, and a minus. Let's try that again. 2 times 4 is 8, plus 12 is 20, minus 8 is 12. And that equals 1. The limit equals 1. Now, since I so regretfully left out one of the major properties of limits at the beginning, before I close down this particular part of the lecture, I'm going to put the properties back up with that other property listed as well. Okay, here is my amended list of properties of limits. First, the limit of a constant is equal to the constant itself. Here's the joker that I forgot before. Here I have the limit of a constant times a function. And that turns out to be the constant times the limit of the function. Visually, what that means is that if we have the limit of a constant times a function, we can take that constant and move it out in front of the limit sign. So, the limit of a constant times a function equals the constant times the limit of the function. We can take that constant factor and move it out in front of the limit sign. Third, the limit of the sum or difference of functions is equal to the sum or difference of the two limits. And what that means is that if we have the limit of the sum or difference of functions, we can compute that limit term by term. Compute the limit of the first term, compute the limit of the second term, then just add them or subtract them. Fourth, the limit of a product is equal to the product of the limits. And what that means is that if we're computing the limit of a product, we can compute the limit of each factor first and then multiply the two together. And next, the limit of a quotient is equal to the quotient of the two limits. If we're computing the limit of a quotient, we can compute the limit of the numerator and compute the limit of the denominator, and then divide. And that works provided that the limit of the denominator is not 0. As long as the limit of the denominator is not 0, this works. And then last, if we have the limit of x raised to a power, we can just plug in the number that x is approaching. Okay, keep this list of limits somewhere. If we're going to be spending a lot of time in mathematics, if we're a math major or physics or pre-engineering or something like that, it would be a good idea to keep this list of properties handy somewhere. Now we're on to new horizons, and very significant horizon too. Okay, on to newer and greener pastures. And this topic that we're about to discuss is a major topic in Calculus I and continues to be a major topic throughout calculus. We're going to talk about a tangent. And the first thing that we do is we define a tangent line, or a line tangent to the graph of f of x. And here's our definition. Given a function f of x and a point x of 1, f of x of 1 on the graph of f of x, the line tangent to the graph of f of x, or the tangent line to the graph of f of x, at the point x1, f of x1, is the line that does two things. First of all, it contains the point x1, f of x of 1. And two, it has the same slope as the graph at the point x of 1, f of x of 1. So the tangent, or the tangent line to the function at the point x of 1, f of x of 1 is going to contain this point x of 1, f of x of 1. And the tangent line will have the same slope as the graph right here at that point. Here's our tangent line. And notice, first of all, that the tangent line does contain the point x of 1, f of x of 1. And notice that right at this point x of 1, f of x of 1, the slope of the tangent line is exactly the same as the slope of the graph of f of x. If we took this little region right here and zoomed in on it, magnified it about 20 times, this is pretty much what we'd see. We'd see the graph of f of x, and then we'd see the tangent line. And they'd pretty much be one and the same thing. Same line, same slope. So right at this point, the point that I'll call the point of tangency, right at this point, the line tangent to the graph, or the tangent line to the graph, and the graph itself have exactly the same slope. So that's what we mean when we say the line tangent to the graph of f of x, or the tangent line to the graph of f of x. Or a lot of people like to abbreviate it even more and call it the tangent to the graph of f of x. And whatever you want to say is fine. Now, how does this relate to calculus? In a second, I'm going to tell you what a major goal of this course is. Okay? Let's get this out in the open right now. A major goal in Calculus I. A major goal in Calculus I. Given any function f of x and any point x1 f of x1 on the graph of f of x, compute the slope of the line tangent to the graph of f of x at the point x of 1 f of x of 1. Given any function f of x and any point x of 1 f of x of 1 on the graph of f of x, compute the slope of the line tangent to the graph of f of x at that point. Major goal. That is a major goal. So after you watch this video, remind yourself a couple of times of what our major goal in calculus is, because this is a biggie. Now, having said that, let me put your fears to rest, because you might be thinking, well, why do we want to do that? I don't understand. Why do we need to do that? Let me assure you, at this point in the course, there is absolutely no reason at all why it should be obvious to anybody why this is something that we would want to do. So don't be thinking, oh, I should understand why it is we need to do that. At this point in the course, it is not obvious at all why this is something that we would want to do. So please, for right now, accept on blind faith and on my word that this is something that is going to be very important. But be assured that if you don't know why this is a good thing to do, that's fine. At this point in the course, nobody should have the slightest idea why this should be a good thing to know how to do. Unless we've had the entire sequence of calculus courses before, and we're just sitting in on a refresher. If we've had calculus before and we're just sitting in for a refresher, okay, you'll understand why this is something we would want to do. But if we haven't had calculus before, and perhaps even if we have had a little calculus before, it's not obvious at all why this is something that we should want to do. Now, the first thing we're going to do is just try a few things to figure out how we can accomplish this goal. Okay, here's our function, y equals f of x, and here's the graph of the function. We want to be able to compute the slope of this line, the tangent line to the graph, at the point x of 1, f of x of 1. Now think about it. How do we compute the slope of a line? Think back to college algebra, or maybe to Algebra 2 in high school. And remember, we represent the slope with the lowercase letter m. So we have this formula. The slope m equals, what is it? y2 minus y1 over x2 minus x1. Okay, we remember that much. Let's see, what are y2, y1, x2, x1? See, if we think about it, these are the coordinates of two known points on the graph. Yeah, x1, y1 and x2, y2 are the coordinates of two distinct points. Distinct. In other words, they can't be the same point. x1, y1 and x2, y2 are distinct known points on the line. Well, looking at what we have here, it looks like we're at a bit of a disadvantage. We only know one point on that tangent line. That's a problem. In order to compute the slope of a line, we need to know two distinct points on the line, and we only know one. We only know one point on this tangent line. Okay. Well, let's go to plan B. Well, our first attempt at computing the slope of the tangent line to a graph didn't work, so we go to plan B. And in order to put plan B in action, we have to define something. We have to define secant. So here's my definition. Given an arc, or a curve, and a point P on the arc, a secant is a line segment that joins point P with one of the endpoints of the arc. So here's a secant. It joins point P with one of the endpoints of the arc. Here's the same arc and the same point P. Here's another secant. It joins point P with the other endpoint of the arc. This idea of a secant is going to be something that we use in our plan B of trying to compute or at least approximate the slope of the tangent line. Okay, here's our plan B. Remember where we are right now. We have a function f of x and the graph of the function f of x, and a point on the graph of the function f of x. The point is x of 1, f of x of 1. And we want to compute the slope of the tangent to the graph of f of x right at this point, x of 1, f of x of 1. We're not able to compute that directly or even approximate it directly. So here's our plan B. First of all, pick a point, x of 2, to the right of x of 1 on the x-axis. Okay, I can do that. Pick a point, x of 2, to the right of x of 1 on the x-axis. Good. Next, plot the point, x of 2, f of x of 2 on the graph of f of x. Okay, I can do that too. Here's x of 2. So here's the point, x of 2, f of x of 2 on the graph of f of x. Third, construct a secant joining the point x of 1, f of x of 1 to the point x of 2, f of x of 2. So we construct a secant joining this point with this point. Yep, I think I can do that. Okay, we constructed a secant, and now use the slope of the secant to approximate the slope of the tangent. And remember we said that by convention we use the lowercase letter m to denote slope. So I'm going to call the slope of the tangent, I'm going to call that m sub tan. This is the slope of the tangent. And it's my hunch that the slope of this tangent line is going to be approximately the same as the slope of the secant. Not the same, but maybe close. So I'm going to approximate the slope of the tangent with the slope of the secant. So I'll write m again for slope, SEC, slope of the secant. Now, why would I want to do this? Beggars can't be choosers. I got to take what I can get. And this secant has a property that the tangent line doesn't. Namely, I know two distinct points on this secant line. This secant line contains the point x of 1, f of x of 1, and it contains the point x of 2, f of x of 2. I know 2 points on the secant, so I'm going to use the slope of the secant, which I can compute, as an approximation to the slope of the tangent. So let's see, how do I compute the slope of the secant? Didn't we say earlier that it was y2 minus y1 over x2 minus x1? Change in y over change in x. So here's y2, f of x2. Here's y1, f of x1. And the change in x, x2 minus x1. x2 minus x1. This is our plan to use the slope of the secant, which we know how to compute using this formula, to approximate something that we really, really, really need to know, which is the slope of the tangent. So this is our plan B. Mull this over, ponder this over, because in our next lecture we're going to pick up right here and we're going to run with it. And remember something, a major goal in Calculus 1 is to be able to compute the slope of the tangent line to the graph of any function at any point on that function. This is important. And the way we're going to do it is we're going to create a secant and compute the slope of the secant and use that as an approximation to the slope of the tangent. And we will continue this tomorrow.